Okay, good evening, everybody. Welcome back to this penultimate Our Universe Revealed of the end of the semester. It's terrifying saying that when it's April, and it's like we're nearly done for the summer, and it snowed last week. So, we're getting there. We're back in 2 weeks' time with the final talk. But tonight, it is my pleasure to move on from astronomy and particles and neutrinos that we had 2 weeks ago to doing more really astronomy in some respects with nuclear fusion from stars. It's my pleasure tonight to welcome Professor Manoel Couder here. He is a member of the nuclear physics group here at Notre Dame. But as he's just been telling me, I pulled his description off the website earlier, and he's like, well, I don't really do that second half of it anymore. So really what he's telling me is he does nuclear astrophysics. And as I said to him, I'm like, that's because astrophysics is the coolest thing that everyone does. Some of the professors in the audience will probably hit me tomorrow when they see me saying that. Tonight, he is going to talk to us a little bit about a technology here on Earth that astronomers are very familiar with, nuclear fusion. It's what we see powering all of the stars, the sun, most of those sources of light we see in the night sky. But the question is, can we develop it here on Earth? Because it would be an immense source of power. And so with that, I'm going to hand it over to Manoel. Let's give him a nice warm welcome.
Thank you. So Jonathan gave half of the talk already. So let's skip to the second part. I start with this figure here, not because it's a promise that I'm going to actually talk about the technology that is hidden behind everything you see there, but because I'm going to sort of address the big picture of it. That's the, or not. That's the formal title, but we don't need to stick to that. I'll speak about all the stickers on it in a second. So before we start, I think it's important to ask an important question. We are in Indiana, so I picked them from Indiana only. What is the closest star from us? So yeah, so that was sort of where I was going with this. I started with Indiana. There's the Jackson family from Gary. And then from Mishawaka, thank you, driver, thank you. And then you can pick the rest, but I verified they are all originally from Indiana, but I'm talking a little bit further away, but not that far away. So indeed, the closest star from Earth is our sun, and our sun is being viewed more and more in various ways. And very recently, I believe it was a week or two ago, those images were published coming from the solar orbiter. And those are various views of our sun at different temperature corresponding to looking at different type of element. And yes, this is our closest neighbor. The same solar orbiter provided a very, very high resolution image of our sun. It took me a while to download it. I'm impressed that the slide turned so quick. This is one of the highest resolution image. It is reconstructed, so it's 83 million pixels, but those are stitched images. If you pay some attention on the top right, there is a little glitch, or more precisely, I call it home. This is relative to our sun, this is the size of Earth. Having a feeling about that relation between the size of our sun and Earth is very important, especially when we think about potentially developing technologies that mimic the size of these things there. And we'll come back to that. Our sun is the source of a lot of things. For us, it's source of life and critical information. If we look at the flow of energy coming straight from it, what we can see is that about 30% of the light coming from our sun is reflected directly. Next to that, 70% is being split in two branches, one that converts directly in thermal energy, and then the other part is contributed to evaporating stuff. And that evaporation store water in our atmosphere and move things. And then there's a tiny little bit, 1%, that contributes to solar energy, as we talk about it, to make renewable. That's energy of the wind and also some current. A tiny, tiny, tiny little bit through photosynthesis, which is a terribly inefficient process, by the way. So if people in the room try to reproduce that, please improve it. Contribute to making plants that animal eats. Both of them somehow need to reach end of life and decay. And through the process of their decays, part of it is trapped and end up as, I use it as fossil fuel. We call it as hydrocarbon somehow. And part of the decay is basically re-emitted as thermal energy. And all of that somehow is radiated in the universe as infrared radiation. And so that's the whole system. Thinking about our sun and of humanity, humanity is using 18,000 billion joules. It's a unit of energy. It's not important, every second. While the sun to Earth, I'm not talking about at the surface of the sun, I'm talking about what reaches Earth, is providing 174 million billion joule per second. So that's sort of the ratio of what comes from our sun and what we are using. Okay. Now, I am not here to claim that we have solved our energy problems and we can go home. 7 minutes was a short talk. I'm only saying that sometimes it's interesting to remember the ratio. There is a lot of energy that is being used in different ways, and those ways do not contribute to make power for humanity. I just wanted to sort of plant that in your head. Now, all of that energy, and it's a lot, come from somewhere. Jonathan told you, he turned that into astrophysics, but the reality is it's pure nuclear physics. Okay? The thing is, for the longest time, since the beginning of humanity, humans have been using their top knowledge of technology to say, I know what makes the sun shine. And so for the longest time, it was wood. You were burning wood, et cetera, et cetera. So once we were able to do some calculation, we could look at the way the sun was shining and say, okay, how long would the sun live if it was wood of that size and that whole thing? And then there was an upgrade. There was discovery of coal. And so it cannot be wood. It must be coal because it's more efficient. And really, there was sort of an effort to always try to explain and where it was coming. The reality now, there was a detour through gravitation, but the reality now is that we know it's from nuclear physics. And the nuclear physics here is that in the core of our sun, about 10% of the mass of the sun there, in there, 4 atoms of hydrogen, for nuclear of hydrogen, fuses somehow into a helium nucleus. And that fusion is what makes our sun shine through something that you may have heard about in the past, the E = mc square relation from Einstein. And the way it works is that if you look at the mass of those 4 hydrogen nuclei and the mass of the helium nuclei, there's a tiny, tiny imbalance. And that imbalance, you can view it is here. The 4 hydrogen nuclei alone are heavier than the helium nuclei, which is made of 2 neutrons and 2 protons instead of the 4 protons of the hydrogen. And so that small mass difference is what you plug into the mass of E = mass times speed of light square to get energy out. And that tiny, tiny little difference, it's what makes the sun shine. Now, it's not really 4 nuclei of hydrogen. We are talking about much, much, much more, and we are going to talk about number in a second. But I need to tell you how that whole thing is proceeding. First, because I'm a nuclear physicist, and so I want to sort of flash that. And 2, because it's going to be important to see, we want to make a star shine on Earth to fuel and to power population. We need to think about how it works in the star. And The way it works, I think, is my only technical term, the PP chain. It's the PP chain, it's a name, it's not more important than that. The PP chain is what fuels the sun. Now the PP chain starts with the fusion of two protons. I promise you 4, and I will bring you 4, it's coming. But those two protons somehow need to fuse and stick together. And more importantly, they need to stick together long enough so they can capture other things. The thing is that when two protons meet in the core of a sun, the odds are totally against the idea that they do anything but just bouncing back and go their own merry way. What's happening is that most of the time, nothing happens besides just a bounce. In reality, it takes that many collisions. You can count them. There is 28 zeros. So 1 in that number chance that when two protons meet in the core of our sun, they fuse. This is not very much. So this 1 followed by 28 zeros. So that doesn't help very much. The good thing is that very, very small probability is completely compensated by the sheer amount of protons that the sun is hosting. In first approximation, it's 1 followed by 57 zeros. That's the number of protons that is in the core of our sun. So that 1 in 10 to the 28, 1 in 28 zero is not completely impossible. It's still very important because scientists estimate that our sun will live the way it lives for the moment for about 10 billion years. If this reaction there was even 10 times faster, our sun would have, first approximation, live 1 billion years. So that was 5 billion years ago. So the sun as it exists would have died 4 billion years ago, way before the beginning of life on Earth, let alone us. And so this tiny little probability there is highly critical. And that's what gives the sun its long life, and that's very important for our existence. Now, when those two meet, most of the time they bounce. When they don't, there's a tiny probability that a reaction that I'm not going to enter in, you heard about some of the particles that are emitted there 2 weeks ago. There's a neutrino and then there's a positron. They merge one of the two protons through a very weak processes, convert into a neutron, and we end up with what we call an isotope of hydrogen called the deuterium, okay, made of 1 proton and 1 neutron. It's the number of protons that gives the chemical properties to the element. So this is still a hydrogen, but it's hydrogen 2, because there's 2 nucleons in it. And so we can go around. Now we have fused 2 protons. We still don't have a helium, but we can duplicate that reaction so that now we have 1, 2, 3, 4 protons ending up with 2 helium-2, hydrogen-2, or deuterium. Okay? Still not the helium that I promised you. Worse, I told you 4 hydrogen convert into a helium. Well, there is a bypass there that I need to talk about. Turns out that 2 more hydrogen are needed to collide with those deuterium to create an isotope of helium called helium-3. And only then do we end up, when those 2 fuses with each other, with our helium that I promised. Now, if we count together 1, 2, 3, 4, 5, 6 protons, but then 2 are re-emitted back to the medium, and so we only use 4 protons at the end, create our helium. Okay? That's what's happening in the core of our sun. Now there is more complication, and there are people in the room here that will tell you much more about those complications. But if we stick together, this is what's happening. 4 protons somehow make a helium-4. Now we were talking about that tiny probability. Let's look at that into number. Every second, about 9 billion pounds of mass is converted into energy. Okay, so we go from that tiny little probability to have 9 billion pounds loss, if you want, in mass, convert it into energy. That gives you the amount of energy that is being converted every second. That's highly critical for how our sun is working. Now I'm telling you all of this because I'm actually super excited by everything that's happening in stars from the nuclear point of view. I'm working for the Institute for Structure and Nuclear Astrophysics and the Nuclear Science Lab. It's funded by the National Science Foundation. It's also your tax money, and so we like when you come and visit us. So we are at the heart of the campus. Shoot me a message and I'll be happy to give you a tour. And in there, what we do is a lot of nuclear physics, and part of the nuclear physics we do is indeed what we call nuclear astrophysics, which is studying the nuclear reaction that fuels the stars, that provides the energy, but that also make the element that we are made of. And that really excites me a lot. It excites me a lot, and even more because we actually have a lab here on campus. We have 3 accelerators here, plus 1 in South Dakota. You know, Notre Dame is expanding. And as I say, we are mainly studying fusion reaction of stellar interest. We have 3 accelerators, that vertical one here, that is right now working for me. I have graduate students studying fusion reaction between helium and nitrogen. Okay, and I'm going to go back to them right after. And we are using this line there that I call my baby. It's called St. George, but this is not the subject of the talk. We have another larger accelerator there and the third one here. And together we are 9 faculty doing nuclear physics research in that laboratory. All of that is exciting. I could talk about that for hours, but that's not what we are here for today. Why? Why would we want to mimic the way stars works here on Earth? I'd like to say I'm extremely comfortable with silence. Efficiency? To harness the power? Other reason, other idea? It's clean. We can talk about clean as well. I mean, sorry? There's a lot of it. There is a lot of it. We will have to talk about it in a second, but yes. Sorry? You can power rockets with it? Absolutely. Other idea? We'll talk about that in a fraction of a second, but only for a short amount of time. Okay, so what would be the challenges? I think that by telling you about the sun, I sort of also expose some potential challenges that could come, and you may think about others. How would we deal with the number of interactions on Earth when we have to have a sun that big to have the number of reactions that fuels the sun? That's an important question. What else? Control it. Okay. Confine the temperature. Indeed, the core of our sun is burning at hundreds of millions of degrees. The outside of the sun is at about 15 million. So there's some interesting question there too, indeed. Make it safe and clean. Okay, I think that I had a list just in case. There is that probability that you address saying, okay, we need the whole sun to actually get something going. How are we going to deal with that low reaction probability? Well, turns out what we need is the sun. Good luck with that. So how are we going to actually get the sun on Earth is an important question. There are all the questions about temperature, how to handle it, or to make it safe, or to sustain it. How do we capture the energy is another question, because what we have is mostly moving particles. Is it clean? Is another question. So I'm going to spend a little bit of time talking about the first one. How do we go around that extremely low reaction probability? Because, as I told you, basically you need so many elements, so many hydrogen, so many protons to collide every second to get energy like in the sun. How are we going to do that? Well, we are going to use human ingenuity and a gift of nature. We are going to go around. We are going to change the nuclei that are reacting. We are not going to do like the sun is doing. So it's a bit cheating, and it has consequences. But what we are going to do is that we are replacing the two protons, the original two protons that I talk a lot about. We are going to replace them by heavier hydrogen isotopes. So we need to find them. So those are the deuteriums that I told you about. Those exist in nature at a very small number, 0.015% of the number of hydrogen that I told you about. So yes, indeed, that's one way. And then we will need another one. And so those two are the deuterium, 1 proton and 1 neutron, and the tritium, which is 1 proton and 2 neutrons. This replacement has consequences, and we are going to talk about it. The way it goes is that we fuse a hydrogen 2, the first one, and a hydrogen 3, the second one, 1 proton and 2 neutrons. Those two, when they fuse, create helium, just like in the sun, energy, but they release a neutron at a certain energy, a neutron that is flying away, okay? And that is the way we are bypassing that very, very weak and improbable reaction that is starting the thing in the sun, is by using a reaction that will have a higher probability to react. Actually, that probability is so high that anytime you make deuterium or tritium in the sun, it disappears immediately, okay? We are going to use that, and that's that fusion that will give us the interesting thing. Now, there's a new problem. One of the problems is this neutron doesn't make it as clean as we were hoping for, because that neutron, free neutrons, are captured very easily by metal. And when metal capture neutrons regularly, they become unstable isotopes, and so they are becoming radioactive. You have a question? I'm going to come to that. So the question is saying, where and how am I going to find deuterium and tritium? That's very important. This neutron is going to be important to that question, and I'm going to get back to that. The deuterium, there's other ways to do it, and I promise I will address that. Okay. Turns out that there's another secret, and that comes to your question. The tritium is unstable. So even if you make a bottle of it, if you wait long enough, it will be gone. And that's a problem. So it means that somehow we are going to have to make it.
I'm sorry, I don't know what everything is.
Oh, it's a unit of energy. And all you can think about is that indeed, those things contain motion, and that motion is the energy. And as much as we do a lot of it, everything will be providing what we need, okay? The fusion of 4 protons into a helium in the core of our sun produce about 24 of those MEVs. And you need a lot of them to get what we have right now. So just for a scale. So we need to make them. Addressing your question, deuterium is 0.015% of the hydrogen on Earth. One way to do it is to filter the seawater. Some of you may have seen the movie, I had the heavy water movie. Let's forget about it. Filtering the seawater by looking at the mass of the molecule of water is the way to go. So water is made of H and then 2H and an oxygen, okay? If one of the hydrogen is a little bit heavier, the molecule of water will be a little bit heavier. And by passing that water into a separator, a mass separator, you will be able to get water molecule, heavy water, that contains that deuterium. So That's one thing we can do. No, it requires energy, it requires a lot of things, but of course we are providing the source of energy eventually. The tritium, on the other hand, needs to be done fully artificially. Us humans need to create something that will make it. One way to do it is the reaction neutron plus an isotope of lithium called lithium-6 that release our favorite tritium that we need and helium. And now we just need to put this hydrogen tree, this tritium in a bottle, and everything will be fine. This can be done in our existing reactors, those dirty fission reactors that makes waste, et cetera, they release a lot of neutron. If we put lithium-6 close to it, well, you will be able to create tritium, and that's how we do it in the US for the moment. I'll talk about why we are doing the tritium, but you have an idea already. Alternatively, you could use accelerator, not very efficient, but you could do it. And finally, if you create a fusion reactor that we are dreaming of, that fusion reactor that is the fusion of deuterium and tritium releasing helium and a neutron, if you surround that reactor with lithium, it will naturally breed tritium. And so once you have put your initial load of tritium, there is a chance that you will be receiving back your tritium through a nuclear reaction on lithium-6. This is an optimistic view of the fusion reactor, by the way. So, did we ever do it? Did we ever use it? Did we ever fuse it? The answer is we do that all the time in the laboratory. I mean, I promise you it is done all the time, but I also promise you we are burning a lot of energy to actually make those. It is not a fusion reactor. It is not something that will provide energy, okay? We need much more energy than what we do. And then, of course, we already talked about it. There's a thermonuclear bomb and the obvious image that goes with it. So in the early 50s, after the two bombs on Japan, there was a debate, and eventually President Eisenhower gave the authorization in 1951 to start research. And the first test that was done in the desert in Nevada of a thermonuclear bomb, which is a bomb that provides most of its energy through the concept of fusion, the fusion of deuterium and tritium. The first test was done in 1952 and was about 10 times more, provided 10 times more energy than the bomb we sent on Japan. So we did use fusion already, and we are still using it. So what we have not accomplished is a controllable, sustained fusion energy production, producing energy for humanity consumption. So what will it take? Okay, because there's a lot of problem. Let's talk about what's going on. Well, we need to contain deuterium and tritium at very high temperature. Because of those high temperature, hundreds of million degrees, we need material, solids that will be able to somehow control and support those temperature or close to those temperature. And we will have to surround the whole system by equipment to gather the energy. Now, this part is sort of the less worrisome part. Those MEVs that you were asking for, this is motion energy. We call that kinetic energy. If we stop those particles in, say, water, the temperature of the water is going to rise. And the last 200 years of evolution of our industrial complex has been successful because we were very good at boiling water. I mean, boiling water is what humans are the best at. This, I mean, started with the steam engine, et cetera, but the current nuclear powers is actually just boiling water as well. And so there's nothing different there. So how do we contain the deuterium and tritium, and then eventually how do we heat it? Well, we use a state of matter that we call plasma. And just like fusion of deuterium and tritium, making plasma in the laboratory is nothing new. I mean, this is a picture that I could have taken today in the nuclear lab at Notre Dame. I didn't. This is a colleague of mine who provided it to me, but it's coming from the nuclear lab as well. This is a bottle, a quartz bottle, in which helium is being injected, and then high power radio frequency, like a fancy antenna, and the antenna is actually those coils that are turning around the bottle, are sending energy into the bottle. The bottle is surrounded by two magnets. And so what's happening is that when you send energy, electrons from the heliums are being dissociated from the helium. They start to move because they get energy. They start to heat the medium, but they bounce on the side of the bottle. And so they are contained into that bottle. And so this bluish light there is an expression of the quantum mechanics that is happening here. And we are not going to talk about that, but this containment in a bottle of a very, very cold plasma is done every day in a lot of places, okay? So making plasma, that soup of electron and ions, is absolutely possible. The containment, it's achieved, this magnetic bottle, if we want to make a big reactor, this is achieved in various ways. One way use magnets, just like for this bottle, and others use pressure. So let's talk about those magnets. The one that everybody knows about is a magnet called a tokamak. It looks like a donut to me, so I stick with it. The idea is to put this bluish color plasma inside a big circular bottle, establishing a current of that plasma that is circulating through that bottle, injecting those radio frequencies that heat the plasma, making sure that the plasma is not touching the wall to avoid heating the solids that are surrounding it, okay? And so by keeping the plasma surrounded by vacuum, contained into that magnetic field, you can reach the temperature that you want. And that is being done. Not to the point of making enough energy, but that is being done. The alternative is in a big, big bottle called a vacuum chamber. This thing here exists. It looks weird, so I took human being in front of it just to prove that there's actually it. This chamber is about 30 feet diameter. And in that chamber, huge pressure in the form of lasers is put on a tiny, tiny, minuscule amount of deuterium and tritium that is smaller than the tip of my finger. The whole system looks like this. This is called the National Ignition Facility. This is in California, in the Livermore National Lab. The 30 feet diameter chamber is there. All those red lines there are 192 laser beams that are all pointing towards the center, creating a system of pressure. So the whole system is called inertial confinement. So it's somehow you confine your plasma, you heat your plasma, and you confine it through those lasers. But those lasers need a lot of power. So much power that that whole system there are amplifier banks for those 192 lasers. The size of this thing there is 3 football fields. Okay, so that takes a little bit of space. By the way, this here is a breakout view of the whole system at the time where Governor Schwarzenegger of California was visiting. There was a very realistic equivalent image of that with a breakout view there. And Governor Schwarzenegger asked, do you have to rebuild the building every time you do a test? And so no, the answer is no, you don't have to rebuild the test. So this system is another way to confine the thing. Now, one of the issues of this system is that the quantity of deuterium and tritium that you have in this thing here is minute. You really don't have the much to do energy, but you can learn a lot. And actually, we are going to talk about that. So the containment is critical, and we talk about it. We definitely want more energy out than what we put in. After all, that's the whole idea. 100 million Celsius, that's 180 million Fahrenheit, must be reached in the plasma. This is phantasmagorical. This is really huge, okay? And at one point, and that's highly critical, we need to stop having to provide energy to the plasma for the plasma to stay hot. Because if we permanently put energy into it at a rate that consumes more energy than it provides, then why are we doing this, okay? And so you remember that alphas, that helium particle with MEVs associated with it, that moving helium is not moving very far. But what is hoped is that motion of that helium into the plasma is going to interact with ions around, with the electrons, is going to slow down and is going to provide its energy to the plasma, keeping it hot. And you'll notice I'm using the word hoping all the time. This helium, so a strap and it needs to provide its energy. Well, that self-heating is finally demonstrated to a serious point. And it actually makes the news in Plasma Physics Nature. That's a more general scientist publication, but then it started going out. Those two publications were in 2022. This was really incredible. Scientific American in February 2022, that's what, 2 months ago. Really, people are very exciting. Turns out that the premises of that announcement that there was an actual measurement and proof that there was ways to demonstrate the self-heating had transpersed in August of 2021. But scientists are careful, they want to repeat, et cetera, et cetera. And all the publications I show you there are actually that. They are after the repeat. But the New York Times went ahead in here, August 18, 2021. They heard about the one explosion that they did at the National Ignition Facility, that there was hints that it was working. And the title is here that I really like. Even scientists who were skeptical of work at National Ignition Facility called the result a success, proving that the helium slowing down in the plasma will self-heat was a very critical moment for the understanding of the plasma. Oh, there, you see that sphere? The laser are coming from really the very top and very bottom. The whole mid-plane of that sphere is surrounded by hundreds of equipment. I'm designing one right now, which is a spectrometer. They have gamma rays cameras. They have pinhole system. They are measuring the number of neutrons. There are all of those things together. And all of that takes, by the way, about 20 picoseconds. So 0 and then 12 zeros and then the 2s. 11 zeros and then the 2. So that's really, really, all of that needs to be measured in that small amount of time. And they use all those technologies that are actually well established. It was established during the Manhattan project, because they wanted to also, during that bomb explosion, that very short amount of time, they also wanted to get the yield out. They also wanted to get all the information of what was going on. And so this is actually new old technology. So they did that. That was really exciting. And then in the scientific community, there is the big thing, which is the ITER project. It stands for International Thermonuclear Experimental Reactor. It's a major project. And the goal is to produce a small, and I insist on the small, power plant fueled by fusion in 2040. So that's, they kick the can down the road multiple times, but for the moment it's 2040. Those large-scale international collaboration, other people have demonstrated that it works. We have Professor Jessop here leading or part of a ginormous collaboration at CERN that have demonstrating that when scientists work together, that works. It would have been nice if ITER had copied what CERN is doing in the type of collaboration. For the moment, ITER is about let's call that in percentage, 25% behind budget. So the quality of the management of the whole collaboration, et cetera, it's really suffering. So the partners are the European Union, Japan, China, Russia, the US, India, and South Korea. And you have the shares there. The EU own 45%, and all the others own 9%. If you do the sum, there is 1% missing, but that's because there's a comma behind the 9. So that's what ITER is. And ITER is a tokamak. I already showed you a tokamak. The chamber in which the plasma is being kept is this big chamber. Just notice the human here, just to have an idea. It's here. Okay. So this thing is big. It's being built in the southern part of France, in a place called Cadarache. It's behind schedule and way behind on budget. But the whole idea there is to demonstrate various parts of technology. Now, it's actually being built. That is a real photo. And it's growing. It's growing significantly. If you're following the news on fusion, you may have heard that part of that chamber, this is really one of the part of that donut, was mistreated at the manufacturing place. And for some reason, the ITER project still accepted it. It was provided to the collaboration. It was dropped into the pit. And at that time, the regulatory authorities that are looking over what ITER is doing said, but if you have a problem, the way you are going to fix that small deformation of the chamber prevents you to take it out. And so now the ITER project is scratching their head about, are we asking the manufacturer to build a brand new part, this part there, or are we going to convince our regulatory authorities that we can make it work despite the problem? So ITER, the schedule originally was 2020 first fusion, by the way. Now it's 2025, full fusion in 2035. The return on investment, or the return into what you put in, is called the Q value. It's the gain. If you get a Q of 1, it means that you get out what you put in. The goal of ITER is to reach 10, so 10 times more than what you put in. It's still very modest, but that's their goal. There's no fusion device that has achieved Q equal 1 yet, regardless of the type of containment. And I gave you 2, but there's a little bit more on the side. The best result was 0.67 last year at the British Jet Laboratory, which is a smaller version of a tokamak compared to ITER. And then at the ignition facility, they reached 0.7. So the comparison between 0.7 and 0.67 is negligible, let's be clear. But that's where things are going right now. So we need to finish. The private sector, well, the private sector is invested. And if you're curious, there's a public paper. You don't need to pay. There's no paywall, nothing. In Nature, and it's actually very well written, that talk about the race to fusion energy, and they summarize the whole system. And they summarize by saying there's officially about $2.4 billion that are declared by various companies. There are all those companies here that have, it's in millions of dollars, of US dollars, and you can see how much they have invested. Their approach is the standard design, Deuterium fusing with Tritium. There are more complex ways, but potentially cleaner because there's no neutrons and no need to make that tritium. There's a fusion of boron and proton that makes 3 helium. It's cleaner, but you need more temperature. And so you kick one method out to bring a more complicated one on the side. And so each of those companies trying something different. Those two comes on top of each other, but that's the promise. The timeline starts in 2020 and finish in 2040. In light blue, this is state-sponsored initiative. You have ITER that is working here with first run in 2025, and then finishing, and then finishing and trying to actually produce energy after 2035. And in between, you have those purple lines of all those companies that are betting on the possibility of succeeding. Maybe. I know that Jeff Bezos has invested in small fission reactor, but I am unaware of his investment in fusion reactor. I'm sorry. I should talk to him. Between ball people, we talk regularly. We have meetings. Anyway, so it means that there are people that really believe that there are money to be invested there. The promise is this one. It was 10 to 20 years down the road, about 40 years ago. You see where I'm going with this. It was 10, 20 years down the road, about 30 years ago, and 20. The reality is that it's still about 10, 20 years down the road today. But there are significant improvement and significant success. And those prospects are really, really exciting. And I stuck to the nuclear physics part and a little bit of plasma in terms of the science. But in terms of material development, in terms of energy gathering, in terms of waste minimization, et cetera, there is a lot of work that is being done in fusion. And I would say, as a fundamental scientist that really believe into answering questions for curiosity, whether or not we ever succeed to make a nuclear reactor using fusion, I think it's worth the challenge to try to achieve that. And with this, I thank you for coming.